Neural networks. The phrase does a lot of heavy lifting these days. It's behind the text you autocomplete, the photos your phone sorts, the model's writing code. But strip away the branding and there's a very concrete piece of math underneath. By the end of these 15 minutes, you'll know exactly what that math is. Not a metaphor about brains. The actual structure. Here's a 3. Sloppy, low resolution, 28 pixels on a side. And you read it without a flicker of effort. You didn't measure curvature. You didn't count strokes. Your visual cortex just handed you the answer. Hold on to how easy that felt, because it's about to become the whole problem. Now here are 5 more 3s. Every one of them reads as a 3 to you immediately. But look at the pixels. Almost none of them overlap. There is no single template you could stamp down and match. Whatever your brain is doing, it is not comparing against a stored picture. So try to write the program. Try to state the rule in words. A 3 has 2 rightward bumps. How bumpy? Where exactly? What about a slanted 3, a broken 3, a 3 that leans toward an 8? Every rule you write sprouts 10 exceptions. So we're going to give up on writing the rule. Instead, we'll build a structure flexible enough to learn one, and then we'll let data fill in the details. Here's what the computer actually receives. Not a picture, a list. 28 times 28 is 784 numbers, 1 per pixel. 0.0 is black, 1.0 is white, and everything in between is some shade of gray. That list is the entire input. Everything the network will ever know about this image is in those 784 values. Time for the one piece of vocabulary you actually need. A neuron, in this context, is a thing that holds a number. That's it. That number is called its activation, and it sits between 0 and 1. Near 0, the neuron is dark. Near 1, it's lit up. Forget the biology. Forget the dendrites. For our purposes, a neuron is a box with a number in it. Now stack them. On the left, 784 neurons, 1 per pixel, holding those grayscale values. On the right, 10 neurons, 1 for each digit from 0 through 9. And in between, 2 hidden layers of 16 neurons each. 16 is an arbitrary choice. I picked it so the picture fits on a slide. The architecture is a knob you turn, not a law of nature. Watch what happens when we feed an image in. Activations ripple forward, layer by layer, all the way to the right. Reading the answer is simple. Each of those 10 output neurons holds a number saying how strongly the network believes the image is that particular digit. You feed in the pixels, activations ripple forward through the hidden layers, and you look at which of the 10 ends up brightest. If the network is any good, the neuron for 3 lights up, and the other 9 stay dim. Which raises the obvious question. Why the layers in the middle? Why not wire the pixels straight to the answers? Here's the hope, and I want to be careful with that word, hope, that each layer picks up on something a little more abstract than the one before it. Let me show you what that would look like. Think about how you describe a 9 to someone who'd never seen one. A loop up top, and a line coming down the right. An 8 is 2 loops stacked. A 4 is 3 straight strokes. So imagine the second hidden layer has 1 neuron for there's a loop up here, another for there's a vertical line over there. And recognizing a digit becomes a matter of noticing which parts are present. But loop is still a big ask from raw pixels. So push 1 layer further down. A loop is just a handful of little edges stitched into a circle. And an edge, a short run of bright pixels next to a short run of dark ones, that is simple enough to read directly off the image. So the dream is a pipeline. Pixels become edges, edges become parts, parts become digits, each layer a small step up in abstraction. Everything so far has been the wish list. Now the mechanism, the part that's actually just arithmetic. We need a rule that takes the activations of one layer and produces the activations of the next. And notice the wiring. Every neuron connects to every neuron in the following layer. So each neuron in layer 2 has 784 numbers coming at it and has to boil them down to 1. Here's how. Assign every connection a number called weight. Multiply each incoming activation by its weight and add up all 784 products. That's it. That's a weighted sum. A big positive weight means this pixel matters a lot and I want it bright. A negative weight means if this pixel is bright, that's evidence against me firing. And critically, nobody types these numbers in by hand. And here's the lovely part. Those 784 weights can be laid back out on the same 28 by 28 grid so you can look at what a neuron wants. Green for positive, red for negative. This pattern says, I want bright pixels in this stripe and dark pixels right beside it, which is exactly the definition of an edge. Pick the right weights and a weighted sum is an edge detector. One problem. A weighted sum can come out as negative 38 or plus 112, but activations are supposed to live between 0 and 1, so we squash. The sigmoid takes the entire number line and folds it into the interval from 0 to 1. Very negative inputs land near 0, very positive ones near 1, and the interesting action happens in the middle. The weighted sum measures the evidence. The sigmoid turns it into a verdict. One more knob. Maybe you don't want this neuron waking up the instant the sum creeps above 0. Maybe it should stay quiet until the evidence really piles up, past 10, say. So you subtract 10 before squishing, which slides the entire curve to the right. That extra number is called the bias, and it sets how hard the neuron is to convince. Weights say what pattern to look for. Bias says how much of it you need to see. Let's count. Between the input and the first hidden layer, 784 times 16 weights plus 16 biases, then 16 times 16 plus 16, then 16 times 10 plus 10. Add it up and this small, unglamorous network has 13,002 adjustable numbers. 13,000 dials, and no human is ever going to turn them by hand. That impossibility is the whole reason learning exists. Writing out 13,000 terms would be absurd, so we compress. Stack every weight into a grid, a matrix, W. Stack the activations into a column and the biases into another. Then the entire layer transition is one line. A1 equals sigma of W times A0 plus B. It looks like new mathematics. It isn't. It is exactly the multiply and add you already understand, written densely, and it's why GPUs, which do nothing but matrix multiplication, turned out to run the world. Which lets me correct something I said at the start. I told you a neuron is a thing that holds a number. More honestly, a neuron is a function. It eats the outputs of every neuron in the previous layer and returns one number between 0 and 1. And zoom all the way out. The whole network is a single function. 784 numbers in, 10 numbers out, with 13,000 parameters shaping everything in between. Complicated? Yes. Mysterious? No. So when you hear that a network learns, here is what that literally means. It means searching a 13,000 dimensional space for a setting of the dials that gets the answers right. Not that it writes rules, not that it forms concepts about threes. That search, gradient descent, backpropagation, the whole machinery is the next chapter. But you can already see the shape of the problem, and that's the hard part. 2 honest footnotes before we finish. First, that lovely story about edges and loops. When people actually inspect the weights of a trained network, they mostly don't find clean edge detectors. They find patterns that look closer to noise. The layered story is a motivation for the architecture, not a description of the solution. The structure is real. The tidy interpretation is optional. Second, almost nobody uses sigmoid anymore. Modern networks use ReLU, max of 0 and x, cruder, uglier, and it trains dramatically better. So that's the whole object. Neurons hold numbers. Weights and biases decide how those numbers flow forward. Stack a few layers, and you get a function from 784 inputs to 10 outputs with 13,000 knobs on it. Learning is the search for a good setting of those knobs. Next time, we go find them.